Today, in this lecture, I'm going to be talking about modeling in science. What are models? What are some types of models? And what are some caveats and assumptions that we have when we're working with models? So first, a little outline to what we're going to talk about. I'm talking about generally what modeling is in the basis of three common types of models. So these are the three basic types of models you'll see throughout science, and then we'll talk about the caveats and assumptions. So first, I want you to think about where you've heard the term models. You probably have certain things that come to mind when you think of models. Maybe you think of model airplanes or model cars, or models that walk down a runway showing off different clothes. Those are not the models that we're going to be talking about in this lecture. We're going to be talking about scientific models. So thinking about scientific models, where have you heard about those before? Perhaps you've heard about them in movies. The Day After Tomorrow and Margin Call are both famous movies that used models to predict some sort of catastrophic event. So The Day After Tomorrow is very fictionalized, where they use a climate model to predict these crazy climatic events. Margin Call is actually based on a true story where a model was used by a bank to predict the early 2000s recession. So that's an actual case of a model being used to actually make a lot of money for some financial industry. You might have also heard of models in the news. So we often hear about climate models, hurricane models, even just your normal weather prediction. Is it going to rain tomorrow, be sunny or not? What's the temperature going to be is a type of model. So the more you think about it, the more examples you can probably come up with of scientific models. There are three main types of models, moving from more basic to more advanced. The most basic type of model is a conceptual model, which is a qualitative model that really just describes a process or describes something. The next more advanced model is the analytical model, which is a quantitative type of model. So this uses numbers and equations to describe a process. And the most advanced type of model is a numerical model, which is also a type of quantitative models using numbers and equations to describe a process. We're going to go through these types of models, moving from more basic to more advanced. So we're going to start with the conceptual model. The conceptual model describes a process qualitatively, so without equations. It's just going to have either an image or a paragraph describing this process. So you probably encounter conceptual models all the time in your classes, whether they're scientific or not, when you hear some sort of model describing some sort of process about maybe the way people behave or a certain scientific equation or chemical reaction. All these are types of conceptual models. It's often the first phase of modeling, so a lot of times scientists will come up with a conceptual model before they make an analytical or a numerical model, so that they can make sure they fully understand all the parts of the model and how they influence the total process. Examples outside of science might include a flowchart, like I have here. So this flowchart shows your decision-making process. If your lamp doesn't work, well, what's the first step? You're going to see if the lamp is plugged in. Based on whether it's plugged in or not, you're either going to plug in the lamp or move on to the next step of troubleshooting to see if the bulb is burned out. And based on whether the bulb is burned out or not, you'll either replace the bulb or bring it to a repair shop to get fixed. So this is a conceptual model because it's describing a process, your decision-making process of trying to figure out what's wrong with your lamp. This is an example of a conceptual model that I used in my research that I published. I was looking at methane. So methane is a greenhouse gas, and how methane gets transported through groundwater in the Arctic to oceans and lakes where it can then vent to the atmosphere. And there's lots of equations and calculations in this study, but I started out the study by talking about this conceptual model that you see there's both an image for, and on the right-hand side a description of how does the methane get from the groundwater to the atmosphere. Well, there's methane production in the groundwater. There's also methane coming into the groundwater from permafrost, and then the groundwater flows and discharges to a lake, and then once the methane's in the lake, it's a lot easier for it to get to the atmosphere than when it was in the groundwater. So I have both a image here describing that process and a description. So these are both examples of conceptual models in science. All right, now we're going to move on to analytical models. So analytical model describes the process quantitatively, so with one or more equations, and it requires well-constrained parameters. What that means is you have to have some ideas of what some of these variables are, what numbers should you plug in for some of these variables? They're relatively simple to solve, and some well-known examples are linear and box models. You've probably encountered linear models in some of your other classes. Here's an example of an analytical model. This is an exponential population model, so this is more of a biology or ecology model. And this describes what the population is at a given time. So we have n there on the left. This is the population at any point in time. This is what you're going to calculate. This is what your model is going to predict. And then we have n naught, which is the starting population, e, which is just a mathematical constant, and then r, which is the birth rate. So, for example, 0.02 means that for every 100 people, the population increases by 2, so you get 2 more people every year. And then t is the time in years. So if you take a look in Excel, where I've actually plugged in this model, you can see up here at the top, I have the equation that I need, and then I have my parameters I need to define. So I need to know what the initial population is, and I need to know what the birth rate is. And then I have my different years and time, so 0 years, 10 years, 20, and so on. And then here is my predicted population as per the model. So this is using the equation to make a prediction of what the population is at that time. So the model here is just that equation, right? And then the prediction that it's making of what the population should be. And that is also plotted here on this figure, which shows the population at any given point in time. So if I change any of these parameters, so let me say, oh no, actually the initial population was not 100, it was actually 500. I can change that in Excel, and then we'll update all of the numbers in my model. Or for example, let's say that I realized I got the population rate wrong. It's not 1 person being born for every 100 people, it's actually 5. Then I can go ahead and I can change that and update what the population rate is and see how that affects the population over 100 years. So you can see that the model really is just this equation that we're going to plug numbers into. And that to use this analytical model, we have to have a really good idea of what these 2 parameters are, the population growth rate, the birth rate, and also the initial population. Without these 2 numbers, knowing what they are, the population model is not going to work, and it's kind of useless for us. Okay. Let's look at another example. This is a linear model, which you've probably seen in a lot of different classes. So in a linear model, it's basically we have a line where any value of x that we plug in, as long as we know what the slope of the line is, which is m, and the y-intercept of the line, which is c, we can predict what the y will be at that point in time. So this is often used in chemical analyses. It's hard to see what some things are in the water. So let's say that there's some caffeine in water. You can't visually see the caffeine, but we can do some different experiments to make the water change color based on the amount of caffeine in it. So maybe we're going to make it turn pink, and we can shine a light through it to see how pink the water is. So the pink, you can make a linear equation that says, okay, well, if it's such a hue of pink, which would be on the x-axis, measured in some quantifiable way, then you can make an equation to say, okay, if it's this amount of pink, that means there's so much concentration in the water, which would be on the y-axis. So in this example here, we know that the slope of the line is 2/5, and that the y-intercept is c, and we can make a linear model that predicts, so we can plug in for x and see what y will be. So we can see from this chart, if we plug in 0 for x, then y is going to be 2. If we plug in 3 for x, y will be 3.2. Or if we plug in 5 for x, y will be 4. So this is, again, just an equation that we're going to plug some numbers in to get a number out. So we're converting from one variable to a different one that we actually care about. And this is used very widely throughout environmental science because a lot of times it's really hard to measure things directly. We have to measure them indirectly, as with the caffeine example, where we're measuring the color of the water to determine how much caffeine is in the water. A subtype of the analytical model is a box model. So box model can also be a conceptual model and an analytical model, as I'll show you in a second. So usually we'll use a figure or an equation to describe the quantity of something going into a box. So the box is something in the environment. The box might be the atmosphere. It might be the ocean. A box could be a school, and it could be like the number of people leaving and entering campus every day. So things going into the box are called a source, and things moving out of the box are called a sink. So let's do an example of water going in and out of a lake. So here we have our box, which is a lake. We're going to do the conceptual model first, and then we will do the analytical model. Think about what could bring water into a lake. Take a second, think about it. Maybe you thought of precipitation, so it could rain. You could get water going into the lake through rain. You could also have rivers entering the lake, bringing water into the lake. Or we could have groundwater actually discharging into the lake that we can't necessarily see. Now what about ways that water can leave a lake? Why don't you think about that for a few seconds? Maybe you thought that water can leave a lake through evaporation, the opposite of precipitation. Or water could also leave the lake through rivers as well. So this is a conceptual model of how water is going to enter and leave this specific lake. Of course, these things will vary based on where you are in the world and what lake you're specifically studying. So we can make this in an analytical model where we set all of the sources of the lake on one side of an equal side and all of the sinks leaving the lake on the other side of an equal sign, and we basically add them up to figure out a term that we don't know. So for example, that would look like this, where rivers in plus precipitation in plus groundwater in is equal to evaporation and rivers leaving the lake. And let's say we know what all these terms are, but we don't know what groundwater is. If we know what precipitation coming in is, and we know what rivers coming are, and we know how much water is leaving the lake through evaporation, how much is leaving the lake through rivers, we can actually solve for the amount of groundwater entering the lake. So these are very valuable tools. If they're relatively well constrained, if you know what a lot of these variables are, what the numbers are for them, you can solve for the missing information. This is very common in biogeochemistry. All right, now we're going to move on to the numerical models. Numerical models are another type of quantitative model, so they use one or more equations to describe them. Usually more equations. All the analytical models we looked at only used one equation, but you can certainly have analytical models that use more. Numerical models do not necessarily have to have all of their parameters well defined. So maybe in that lake example, we just didn't know what the groundwater is. Maybe the numerical model also doesn't know what evaporation is. So you got to figure out two things. Numerical models are usually employed when they're more difficult to solve. So maybe there's 8 equations you have to solve at the same time. Or maybe you have to solve the same equation 80 different times, representing 80 different hours of an experiment. That's going to take a long time to do by hand. So we're going to use a computer algorithm to approximate a solution. So it's not necessarily the actual solution, but we can usually get pretty close using a computer algorithm. Well-known examples are climate models, earthquake models, and finance models. So these are all models where there are a lot of things going on that you have to account for. So thinking about a climate model, you have to know, if you're going to do climate for the entire planet Earth, you have to know what the air temperature is during different seasons, at different points in the atmosphere, because it's going to vary. It's going to get cooler as you go up. You have to know how much sunlight is coming in. You have to know what the ground cover is. Is it mostly asphalt? Is it mostly trees? Is it mostly grass, or is it water? You have to know how many clouds there are, how big the clouds are, what type of clouds they are. There's just lots of variables that you have to account for in a climate model, so they're very complex, which is why we want to use a numerical model, a computer algorithm to solve them. Here's an example of a very common numerical model. This is developed by the U.S. Geological Survey. It is called ModFlow, and it is a model that accounts for groundwater flow in an aquifer or in different areas. So it can account for groundwater flow in a 3-dimensional aquifer in different time steps. So over time, you can see how groundwater flows and how groundwater changes. So you can see that this box here is actually made up of lots of little mini boxes. And there's this equation on top of that that determines the physics-based equation of how the groundwater should flow from one box to another. So this equation is solved for every one of those little itty-bitty boxes for every time step. So they may run this model where each time step is 1 day, and they might run it for 100 years. So you're going to have to solve that equation for each of those boxes 100 times. And the terms are going to update every time as water moves throughout a box. each of those terms or parameters in that equation is going to change. So since this is a very complex model, it's a model that suits well to a numerical solution using a computer algorithm. Here's an example from my research where I used different tracers to approximate how much of nutrients in a coastal bay in California came from 3 different sources. So I was looking at river water, groundwater, and then deep ocean water coming into this bay and determining what percentage for 50 different locations in that bay, for each location, what percentage came from river water, what percentage came from groundwater, and what percentage came from deep ocean water. And I used 6 different tracers to identify these sources. So I have a system of 7 equations that had to be solved for each of the 50 locations. So for this, I used a computer software program called MATLAB to write a program that was able to run different algorithms. Eventually found like the algorithm that worked the best to solve all equations at the 50 locations in the bay. So again, I wasn't going to do that, especially since I had to run this multiple times to assess the sensitivity of the model and make sure that it was working correctly. That was not something that I wanted to do by hand, so I was able to approximate it using a software algorithm. So some caveats of models. All models come with assumptions, so these are things that are kind of understood that must be occurring for the model to be true, to be accurate. And the model shouldn't be used if the assumptions are violated. So if you think you're going to bake a cake, right, the assumptions of the models are that you're following all the instructions of the cake. So if the cake recipe says that you should set the temperature of the oven to 375, the assumption is that you're actually going to set it to 375. If you set it to 200 and you follow all the other instructions the same, you're not going to wind up with a cake. You're going to wind up with a wet, blobby mass of flour and milk and eggs. So you need to really make sure that you understand what the assumptions are of models before you use them and that all of the assumptions are met. And if they're not met, you might need to use a different model. And when you're reading a paper or reading about a model in a scientific journal or at a presentation, the model assumption should be clearly stated. So if someone's using a model, they should say, hey, these are the assumptions that we're using when we use this model. If we go back to the population model that we use, the exponential population model, we're predicting what population is of flies or rats or something. There are some assumptions inherent in that model. So it says there's no immigration or emigration, so no one is moving in or out of that population. Also, the growth rate does not change, so people can't suddenly decide, or flies can't suddenly decide, we don't want to have kids anymore, we're going to stop having kids. The same growth rate has to occur throughout the entire duration of the model. So those are 2 assumptions of that model. So as I've talked about, you may see that there are models everywhere. I would encourage you to think about what are some examples of models that you use in your everyday life. Are they conceptual models? Are they analytical models? Are they numerical models? Think about this as you go through your classes or as you go about your daily life. The more you think about models, the easier they will be. The easier they will be to implement when you need to. So some common examples would be any math equations that you use, cooking or baking recipes. What do you do if your internet stops working? What are the steps that you move through? Or if you have a specific sport you play, is there a strategy, which might be a model, or a specific play that you use to advance the ball down the field?